Good morning. So, today I want to talk about the Ouroboros. This is the ancient world snake that circles the world and represents chaos and the unknown. Although today I don't think that's actually what it's going to represent, because the Ouroboros is also the snake that eats its own tail and cycles around forever. And I want to talk about how that's a little bit like folds and fixed points, and I'm going to get to what that means. And I'm going to talk about how fixed points of functors and folds can help us to build a composable type checker and type inference engine that fits together a little bit like your favorite Legos. So, to get out of the world of metaphor a little bit, here's fix. The fixed point of some f, where f is a type that a type of kind star arrow star, is fix of f applied to fix f. So hence the Ouroboros. If you can see, it's not scales on the pattern, it's f's circling around forever. Because fix of f is isomorphic to f of f of f of f forever. So you're probably wondering where I'm going with this. And I have to say, it's going to be a little bit of a long punchline in this in this talk. There's a bunch of different pieces that I want to put together, and then at the end, I'm going to show you how all the pieces come together, like, as I say, Legos. But hopefully the snake will be our guide and won't lead us astray into the chaos beyond the worlds. So we'll see, right? So fix. I can take the fixed point of some f. And I can talk about an f as being the shape of the functor, or rather the shape of each level of the structure that we're building. Fix says, tell me how each level of something is shaped, and I will show you how the entire thing is shaped if you feed it into itself by having it eat its own tail. And then if I say, well, given one level of structure, here's how I collapse an f of a level of structure into an a, then I will tell you how to take an entirely deeply nested recursive structure and collapse it all the way into an A. So how does that work, right? Like, I say combine, which takes an f of a to an A, and I combine the results of mapping fold combine, which takes a fix f to an A, over the contents of a fix f, which is an f of fix f's. So we get an f of a's, which we then just fold together and get an A. So, okay, a little bit quick and abstract with the type variables. Let's show what it means. So, if I take the fix, capital F, fix of the list functor, then that gives me a type that's like a tree that has any number of branches at any point, because the list shape says that I can have 0 descendants, or I can have 1 or 2 or 3, and then I fill in all of the holes in that functor with all of the places that I can have some kind of recursive structure that descends beneath it. So if I want to count the nodes in such an n-ary tree, I just have to fold with the function 1 plus the sum of all of the results beneath me. So that's to say, if I have the function combine, where combine takes a list of int to an int, by summing the result of all of the ints, so that's to say, sum all of the number of nodes beneath me, and then add 1 to the result because I myself am a node. Then if I fold that across a tree, I should be able to count the number of nodes that are within the tree. So let's try it. Here's an input. A lot of the time, when I'm playing around with this fixed type, one of the things that gets really annoying is the fact that it's a new type, which means that you have this fix constructor that you have to play around with all the time. We're now firmly within the land of I'm talking about Haskell with concrete Haskell types. But you could do this in any language that has a higher kind of polymorphism. So I like to think instead about sort of squinting my eyes and seeing through the fixed constructors to see the structure that's underneath. So here's my tree. My tree looks like this, or more tree-likely looks like this. And I'd like to fold it with the function that I just gave. So what's the base case? Well, the base case is the sum of the empty list is 0 plus 1 is 1. Okay. The sum of the list containing 3 ones is 3 plus 1 is 4, and the sum of the list containing 2 ones is 2 plus 1 is 3, and then I sum 4 and 3, which I think is 7, plus 1 is 8, and indeed there are, if I back up, 8 nodes in this tree. So cool. Folds! And this kind of reminded me of something else that I really like, which is type checking. Because a type checker does a kind of similar thing where it takes the structure of the abstract syntax of a programming language and it walks through the entire structure and it says, well, are these two things type correct? Is this sub-expression type correct? What is its type? Given the type of this thing is that, given the type of this thing is that, and if we combine the two things in this particular combining form within the language, are those two things type correct next to each other? Well, suppose we define our language in such a way that we can use the same mechanism to type check it. So I started poking around at it, and I heard the whisperings of the snake in my ear, and I said, all right, so a term in our language now is going to be the fixed point of this term base functor, where if you look, term of A has an A where every one of the subterms of that term could appear. So a term of A could be a Boolean literal or an integer, or the addition of two terms, or whether two terms are equal, or the negation of a term, or the and of two terms, or an if statement. So one thing to note is that sometimes I might want to fill in a term with things other than other terms. So I'm not just going to be taking the fixed point of a term. I'd like to be able to write a function like check, where I take a term full of types, where I fill in all the places where a subterm would have been with the type of what that subterm was, and I determine what the type of the term itself is based on looking at the subterms types that have been filled in inside of the term. So for example, the type of a Boolean literal is bool. The type of an integer literal is int. The type of the addition of two integers is int. If I try to equate two integers, then the result type is bool. If I negate a Boolean, then the result is a Boolean. If I and together two Booleans, then the result is Boolean. And if I have an if statement where the condition is a Boolean, and the two branches have the same type, then the resultant type is that type. Otherwise, this is not a type correct term. So notice that everything on the left-hand side in this case statement is a value level thing in Haskell. This is actual Haskell code. I'm using capital int and capital bool as data constructors of the type on the upper left-hand side. And what I want to do is I want to take this really natural definition of what it means for any individual level of my term language to be type correct and what its type is. And I want to lift it in just such a way as we've seen with fold to be able to infer the type of an entire fixed point of a term where I've substituted terms into themselves, so I have a recursive term structure. So in order to do that, I know that the resultant type of my infer function is going to be maybe type. So that means that I need to pick a combined function that's going to result in a maybe type. And that, based on the type of fold, means that I have to write some function of type term filled with maybe types to maybe type. But I can do this because if I take the result, which is to say the term filled with maybe types, those are potentially the resultant types of all of the sub-expressions, and I sequence it to pull out the maybe so that now I have a maybe term of type, I can then check that term of type to get back may be whatever the resultant type of the thing is. And then I fold that thing, and I get the type of the thing that I care about. So let's go to the REPL. If I infer the type of an integer literal, it's an int. If I try to add an integer to a Boolean, it's nothing. If I try to have an if statement where the two branches, and this is where the fix noise starts to bug you, right? Because it's fix if, fix be true, fix I1, fix be false. But if you really I don't know, it's like programming in Lisp. You squint enough and the parentheses stop making themselves apparent. Well, this doesn't make sense because the two types don't match in sub-expressions. And if the types do match, then it's just an integer. So we wrote a type checker. Type checkers are folds. End of story. Questions? Except we're missing some things in our language. This is not a language that I would like to write any programs in particular because it has no means of abstraction whatsoever. It doesn't have any variable binding. So let's try to add it, right? So I now can have string variables. I can have let expressions that bind a string variable to some value in some body. But, well, I don't want to do a spotlight search. But what am I supposed to substitute in here? And I just gave you a sneak preview accidentally. Given that I have a string variable, what is its type supposed to be? I don't know anything about it, but I have to manufacture some type for it. So that's kind of problematic because I don't know anything about what its type is. I have to know what its type should have been, given what expression it occurred in. And similarly, with let expressions, the type of a let expression is the type of whatever its body is, but I have to do some action to cause the type of the body to be type checked, given that the variable is bound to whatever the type of the value is. So I want to introduce a new type that I'm going to call env for environment or type checking environment, which is just a mapping of variables to their types that I'm going to maintain. So I'm going to thread it through like so, and I'm going to say, okay, well, the type of a variable is now whatever type it is when I look it up in the environment. And if I can't find it in the environment, then this expression is ill-typed or ill-scoped even. And the type of a let expression is just the type of its body, because that's the type of a let expression. So I can glue things together using this infer function quite similarly. And I say, all right, well, I just fold. Well, I have to, fill in the environments. I have to come up with an environment. I start with the empty environment. I say fold with flip combine map empty. All right, well, plumb the things through. And then everything type checks. So as we know, being strongly typed functional programmers, if it type checks, then it works. But oh, sorry. Now it type checks. So now it works. Right? Everything type checks. We've threaded the environment through. But the thing about implementing type systems is that when you're implementing a type system, unless you get really lucky or you're really clever, it's very hard to make sure that the type system keeps you from implementing your type system wrong. And indeed, let's, ominous music, which perhaps we could procedurally generate. Unfortunately, no actual variable binding seems to have occurred. Now let's zoom back at this, right? So I start with the empty environment, and then whenever I find a variable, I look it up in the current environment. There's something missing. I need to do something a little bit more clever. And in particular, what I need to do is I need to thread through an environment from the top. And when I go from the top of the expression, I need to thread through an environment that shows me exactly what it is I need to thread through the empty environment starting at the top of my expression. And when I find a binding site, I need to expand my environment as I proceed down into the binding site so that I can then type check things with an expanded environment that includes the types that I've discovered. But this is in contrast to the direction that the recursion of fold gives us, because when we fold up from the bottom. So now we want to fold up from the bottom, but in order to fold up from the bottom, we need information that's coming down from the top. And so, my computer was deeply surprised and unnerved. And so something feels like it has to give. So instead of trying to somehow write a manual recursion that does all of this for us, you know, like if you were doing this yourself, you could thread things through manually by writing the recursion yourself, starting with the environment at the top and making it a recursive call at every point where you wanted to do the thing. And it's like, oh, okay, well, we're now losing all of the benefit of these beautiful folds that made everything seem so simple and straightforward and non-recursive, or at least only secretly recursive. So instead what I want to do is I want to do a fold that gives me a function from an environment to maybe a type. So I start at the bottom and I fold terms containing functions from environments to maybe types, to build bigger and bigger functions from environments to maybe types. And as I glue those functions together, I want to eventually find a function that's going to thread through the environment from the top all the way down to the bottom after having folded the syntax of the term to build the function in the first place. All right. So I try to do this, and the way that I try to do this is I'm going to go back to the structure of this infer function that I had before, and I'm going to use my favorite feature, or my latest favorite feature of Haskell, which is typed holes. So because I'm pretending that we're in Emacs right now, even though we're not, I'm going to say that we found a hole, and the hole is of type term of environment to maybe type to environment to maybe term type. So that's to say, if I can find a way to take a term that's full of environment-taking maybe types, and I can take an environment and I can use it to produce a maybe term of type, that's to say, I can take an environment from the top and use it to feed these functions that are waiting for the appropriate environment to give me what the type would have been in that particular environment. Then I can build this whole function that infers things properly by folding up to create a function that threads down. And what I need to do is I need to just say, well, if I have a let expression, then first look at the value type. So the value type I'm going to get by taking val, which is a function from environment to maybe type, and applying it to env, which is the environment that we got passed down from the top. Then I'm going to call body, which is again a function because we're pattern matching out of the let, right? So let is again a term of this functor. It's a term of environment arrow maybe type. So we're going to apply body to the augmented environment that binds var to val type, augmenting the environment that we got passed down from the top. And then we're just going to return a let expression that fills in those types. So now that let expression is going to have those appropriate types. So when we pass it to check, check is going to be able to figure out, oh, well, we just returned that body type. And we've done the binding that we need to do in that body type in so sequencing like this. And otherwise, there are no other binding structures, which means that we can just traverse the term and say, well, whatever you are, you just need the environment that I got, so here you go. And if we thread it together like this, notice I'm using bindings here rather than sequence. We've decomposed inference into a traversal to apply the binding structure of our language, and a fold to check the types in our language, which looks really nicely, except what about lambda? So I'm going to pause here for a second for slow digestion, and then I'm going to move on. Because we're functional programmers after all, right? So we'd like to have functions in our language. This is still a language that I don't really think I can write very many useful programs with because, well, there's not a lot I can really say. So let's add some function types. Let's add some applications and some lambdas. Let's just try to add what we need to make this a functional programming language. The madness from beyond the worlds has been thus far kept at bay. So, all right, so how about applications, right? So if I have an application of a function type to an argument, then provided that the argument of the function type is equal to the argument type that we're actually applying it to, then the result of that application is going to be just the result of the function type. Cool. Now, when I have a lambda, I have like lambda x something. Well, I know that the result type of the function that I'm going to be generating is that something. And its input is going to be it's going to be a type. Yeah, it's going to be a type, but lambda? All right, so I have a very pattern-matching brain. So when I was thinking about this, for some reason, this very bizarre phrase popped into my head, and I Googled it, and I was like, oh, this is a phrase that Ronald Reagan said during the Cold War, except actually he stole it from a Russian proverb. But it's widely attributed to him. And so this is not actually what I want to say. Trust but verify is, I want to say guess but unify. And probably someone said that. So here's a quote that's going to motivate what we're going to do. Because what we want to do is we want to be able to say, it's a type, it's going to go here, and we're going to find out what it is, because when we actually apply this lambda expression to some argument, we're going to know what the argument of the lambda expression should have been. And then we can therefore keep going and type checking. So borrowing very extensively from this really beautiful library by Ren Romano, I'm going to try to build unification. So let's back up. So before I dive into the detour that I just hinted, just to make sure that we all know where we're going, because we're about to like swerve off to the side, and I want to make sure that the long arc of the talk is persistent in our heads, right? So we need to make up a type here. And when we make up this type, we don't know what it is. So we want to make like a placeholder type that says, all right, here's what this thing is. It's going to be some type. We're going to find out later. And then eventually when we find out, we need to percolate that information back and fill in the hole that we've made, fill in the unification variable. And then in the end, we're going to know what the type is. And so through this like action at a distance, we're going to actually find out what types things should have been. But how can we do that? And how do we unify things to begin with? So I, as perhaps some of you have taken an algorithms class. And I remember learning about the union-find algorithm. And I remember forgetting about the details of how the union-find algorithm works, which builds a structure of keeping things unified or something like that. And I remember thinking to myself, I'll implement unification. How hard could it be? I remember how to do this. I've taken an algorithms class. And then I started doing it, and I was like, oh, I don't actually remember how this is supposed to work. So I figured out how it's supposed to work, and I thought, this is obviously not novel. It was invented in like the 1970s or whatever, but there are some beautiful things that deserve to be re-explained and reshared, and so I wanted to talk about it. And also, I like drawing pictures, so I've decided to draw you some pictures about unification. So let's draw some pictures about unification. The point of unification is that I want to be able to have some way that I can say, here's a thing, there's a thing, here's another thing. At some point, I'm going to say, thing 1 and thing 2 have to be equal to each other. And then at some other point, I'm going to say, thing 5 and thing 6 have to be equal to each other. And then I want to be able to ask later, is thing 6 equal to thing 2? Having done all of these actions of squishing. like, can I squish things together into all of these sets that are all equal to each other, and then find out later, okay, what things are equal to what other things? And I want to be able to do this efficiently because as I'm type checking, I'm going to be generating all of these unification variables and saying, aha, well, this is an unknown type, but then this type gets set to be this other type. So now I need to figure out what type this type was, as it was set equal to this type, and then that type was set equal to this type. So I want to be able to do this efficiently. And to do that, I just need to build a cute little data structure that's super imperative, but it's super cool, so I want to talk about it today anyhow. Here's the interface that we need to build this thing. We have a monad called unification. We have a unification variable. We can make fresh ones, which are not equal to anything else. We can, we can find what's called the representative of a unification variable, where the representative is some particular unification variable, and it's going to be, according to this abstract interface, a particular unification variable which is arbitrary but fixed for every unification variable in the set that are all equal to each other. So that's to say, if there's anything in like the transitive, reflexive, like symmetric closure of setting things equal to each other, if any of those things, like in that link of everything that have been set equal to each other, if any of them are equal to each other, then we want to make sure that when we call find, we always find the right thing. That is to say, find returns a unique unification variable that represents all of the ones that have been set equal to each other. So if we want to say in the end whether two things are equal to each other, we just check to see, is this thing equal to that thing? Well, we want to say, are their representatives equal? And if their representatives are equal, then they themselves have been at some point transitively equated. And union just says, let them be equal. They are now so. So I made some unification variables for you. Here you go. I'm going to set some of them equal to each other. And the way I do that is I just arbitrarily pick a direction for a pointer to point. And now when I look up 6, 6's representative is 1 and 3's representative is 2. And now if I want to unify 5 and 6, I find 6's representative, which is 1, 5's representative, which is itself, and I arbitrarily pick a pointer here. And I do the same here. And then if I want to unify 5 and 4, then I just go boom, like so, and find their representatives respectively and add a pointer. So this is cool, this works, and now I can look up, I want to say are 4 and 6 equal? I just follow the pointers and I find that they have the same representative, which is 1. And everything works out nicely sometimes, because sometimes when you arbitrarily set the pointers, you end up having all of the variables point to the same representative directly. And sometimes, when you arbitrarily set the pointers, you end up having things not point to each other directly, and you end up with a pathological case where everything goes around in a circle. And this is still correct, but it is very efficient. Inefficient, rather. And that's not any fun. So instead, we're going to do this thing called path compression. And path compression, what that does is it says, hey, look, isn't there this weird thing where when we find all of the, when we like try to unify two things and we find all of the things along the way that lead up to us finding their representatives, all those things could really just be set equal to that representative, and it wouldn't change who has what representative, but it does mean that we have to take fewer links to get where we're going. And so that means that if we keep doing this every time we do a find, then we just go like sort of, I have a cat, and I just think of like combing the fluff out of his hair or something like that, doing that with pointers. I don't know if that metaphor makes sense to everyone. And so with path compression and this thing that's another optimization that's called union by rank, we can get this ludicrous, very good asymptotic complexity for union find, which is to say it's order of the inverse Ackermann function. Now, so the inverse Ackermann function, the Ackermann function gets very big very fast. It goes like 1, 3, 7, 61, And then, and then Ackermann of the fifth of 5 is a very large number, just like extremely large, just an absolute unit of a number. So that's to say, Ackermann 5 can't actually be represented in the physical universe. If you took all of the subatomic particles and you made them bits, then you'd need many, many universes to represent it. So yeah, this is one of those weird algorithms that has asymptotic complexity of 5. But of course, we don't just want to unify like these sort of atomic things, right? We want to unify things that actually have a payload of a type. So like we've got this deep structure and we find out like, hey, we've got a function and we know what's on the left-hand side of it and we don't know what's on the right-hand side, and we've got another function, and like we've got this recursive structure that we want to unify. So we want to attach a payload to our unification variables. Instead of just having them be atoms, they're now going to hold, potentially, a thing that they're equal to, which we can read. And we can make a fresh one that doesn't have anything in it. And we can make a new one which has something in it. And we can now unify them, provided that we can say, given two A's, how do I smoosh them together or fail if they can't be smooshed? Because some things can't be smooshed, like a function type in a tuple or whatever. So if I say we're to unify with the function that takes strings and concatenates them, and I unified 1 and 2, and I unified 5 and 4, and 3 and 4, then I would get these arbitrary strings that I chose for no reason whatsoever. So ending that detour, or almost ending that detour, I want to show how we can use this unification variable interface to solve our original problem, which, if you remember, because this has a long punchline, came from trying to introduce lambdas to our type checking system. So remember our faithful friend fix. I'm going to take fix and I'm going to make another constructor which holds a unification variable that's like a mutable pointer that wraps around the same sort of thing that ufix is. So that's to say, a ufix is an f of f of f of f, or it could be like an f of mutable pointer to an f of mutable pointer to an f, etc. And that means that throughout this thing, we can have just like holes, where a hole could be filled in with something or not. We have to dereference that pointer in order to find out what it is. And under the hood, we're just using this unification algorithm to efficiently smoosh things together. And we can indeed smoosh things together, because if we define smooshing only on one level, so that's to say, if I can say how to take two types and unify their topmost levels of structure, then I can extend this into unifying all of a deeply nested recursive structure that could be a complicated type. But to do this, I need to make type itself, unlike before, a functor, and take its fixed point. So now I have this match type function that says, if I have an integer and an integer, then unifying those two things gives me an integer. And a bool type and a bool type unify to a bool type. And two function types unify to a function type, provided that the two sub-unification problems of unifying the two inputs and the two outputs are correct. And then I can just lift this function, just like we were talking about before using fold, to unify fixed points of types, so that I then get a unified fixed point of a type in the end. So that was a long breathful of stuff, and now we're in like the maybe T monad transformer on top of the unification monad. But if you squint, it's still the same idea that's going on, and I want to show you how that's the case. So if we have a Boolean or an integer literal, then these things have type bool and int. And then using some helper functions, like this provided function that just asserts these constraints and returns the thing at the end if the things actually do unify, I can say, if I add two things, then provided that both of them are integers, we return an integer. And, you know, scrolling down a little bit, if I have a variable, I'm still doing the exact same thing. I just look it up in the environment. If I have a let expression, I'm just returning the body of it. If I have a lambda, then I just return now the function from the variable to the body. And if I have an application, now yes, no, that's correct. If I have an application, then I just invent a fresh result variable, and I say, provided that the function type is equal to the argument type arrow result, then I return the result. And this looks quite similar to what we were writing before, except that we shoved some of the pattern matching on the left-hand side across to the right-hand side, because now it has to sort of pattern match in a constraint solvey, like unification monad way, rather than just in a like literal Haskell pattern matchy way. And notice that there's still no recursion here. This is still just a flat description of how to unify, of how to type check an individual one level of structure of a term. And it also doesn't describe bindings at all, because we've still factored apart the bindings into a separate function that's just like what we did before, except that the type is a little bit more complicated. But it's not that much more complicated. We've just replaced maybe with maybe t unification. And now in bindings, when I have a lambda expression, this is getting to the punchline of that lambda question mark that we had earlier, I invent a fresh argument type, dually to how I had to invent a fresh result type in the check function. I invent a fresh argument type, and I call the body type, I say take the body of the lambda, and type check it in an environment that augments the variable with this fresh argument type, and then return that lambda expression. And if there are no other binding structures, which indeed in this language there aren't, then we just do a traversal to apply the existing environment to them. So putting these things together, we have almost exactly the same inference function as before, with the addition of a little bit more line noise to unwrap some new types and like run some stuff. The things to note are, what we do is we do a fold. The fold is again taking terms full of functions from environments to maybe types to a function from an environment to maybe a type. And you notice I'm like significantly pausing before I say some of these things, because of course there's some wrappers around and whatever. But you do this, you call bindings on the term in the environment, you get a result, and you check the result in the environment, and that's our fold, which we then start at the very top at the empty environment to get a type. And then at the end, we take the type and we find all of the unsolved unification variables, and we turn them into their integer identifiers, which is called zonking here, which comes from the internals of GHC, because it turns out that there's really no English word for what it means to take a nested type structure and find all the unification variables and dereference them. And so at some point, I think possibly Simon Peyton-Jones was thinking to himself, well, we need a word for this because we're talking about it all the time. So thus the word zonk was introduced into the universe, and I just want everyone to know about that because I think it's cool. So, yeah, it is the sound it makes, right? You just go zonk, 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 like, obviously. So what's left, right? Like, we've built a functional programming language, and we've done so by decomposing binding and type checking, and decomposing recursion and actually verifying what's going on. So now we have a traversal and a fold that are composed together into this alternating way that gives us a type checker. Well, it would be nice if we had like ADTs and pattern matching, but patterns are just like type checking a pattern is just like type checking a term, except that a pattern is a different kind of thing than a term. So you just write another fold. We can have complex binding structures like case expressions or mutually recursive let. And that just means augmenting our binding function. And we'd really like to have useful error messages, because getting a nothing isn't very informative. And then it would also be really nice if we could elaborate our terms instead of just producing, like, what's the type of this term? We'd like to say, what are the types of all of the subterms in this thing? And we can have all of those things that we want. Am I missing a slide? I think I may be missing, oh no, the slide is coming up in a second. So here we go. Here's a little language. It's a strict subset of Haskell. I wrote a little program. It says, take 5 from the infinite list of numbers ascending. And I elaborated it to put all of the types in it. And so here's an example of the sort of thing that we can get out of this inference algorithm. And if I make a mistake, like flipping the arguments, I get a beautifully located type error that tells me exactly what went wrong. And all of that is made possible by composing together functors. So that's to say, we lift the type checker. Because it's been defined in this way that uses open recursion, I can lift the type checker from taking a fixed point of a term to taking a fixed point of a source span and a term, so that we then interleave the source span functor with the term functor. And then at the end, what we can do is we can get all of the nice error information that we want out of it. And through a little bit of extra jiggery pokery, we can get this nice little language. So go learn more things. I like this stuff. Here are some cool references that I think you might want to take a look at. All of these are really worth a read. And thanks.